This voiceover is about entanglement, spooky action at a distance. So famously, Albert Einstein believed that quantum entanglement was spooky action at a distance, and he didn't believe in it. But why? And we'll go into that in just a second. So entanglement is a quantum mechanical phenomenon where the state of two or more particles becomes inseparable and correlated. Entanglement is a theory and a fundamental law of quantum mechanics, and it's also quantum computing's best weapon. Since 1927 and onwards, Einstein and Niels Bohr would go on to have collegial debates about whether entanglement and indeed quantum mechanical phenomena really existed and whether they could actually describe reality. And most accounts of people who were there would say that the quantum theory of Niels Bohr retained the edge during these debates. And during these debates, Einstein came up with a thought experiment that he believed would challenge Bohr and show the illogical nature of quantum mechanics. He said, if you had a single box emitting a single photon, and that photon then traveled far and far away into the universe, it wouldn't make sense that if you measured the box, you would find out some property about the photon. But much to Einstein's dismay, in trying to debunk this idea of entanglement, the idea actually rose to popularity. So let's, to give a formal definition of entanglement, can be thought of as the type of correlation between particles. When two or more particles are initially entangled and put together, they can interact with each other, form an entangled state, and then even if we send a particle, let's say, to the other side of the cosmos, if an observer on one side of the universe decides to measure the property of one of the particles, they instantly obtain information about the state of the other. Or even if they perform an action that changes the state of one of these particles, then the other particle will instantly be changed, instantaneously and regardless of distance. So you can think of it as a sort of funny example as Schrodinger's cat, which can be dead, alive, or both dead and alive. Let's say you adopt Schrodinger's cat's sibling, and you take them home and you look after them, of course, still within a box. And when you take it home, just before you took it home, it managed to interact with its sibling and entangle with its sibling. And then one day when you're at home, you decide to open the box and to check whether the cat is alive or dead. And sadly, your cat is dead. But what's more, because of the nature of that specific entanglement that occurred earlier, you instantly know that sadly, Schrodinger's cat has also passed away. That's what entanglement is like. So the reason Einstein didn't like entanglement was because it violated his laws that were based on common sense. Einstein developed the theory of special relativity almost 2 decades before quantum mechanics in 1905, so more than 2 decades actually, and famously argued that there was a fundamental speed limit to the universe, the speed of light. And so Einstein teamed up with Boris Podolsky and Nathan Rosen in 1933, following Bohr's new physics, to publish a famous paper called the EPR paradox paper. And the core idea of this paper was that entanglement couldn't exist because this meant that these two particles, if you sent them across the universe, would be communicating via the instantaneous entanglement, and that would violate the speed of light restriction. So therefore, they must have agreed upon some sort of hidden value before separating. And that was a very strong theory, but unfortunately, the Northern Irish physicist John Stuart Bell would finally realize a fundamental experiment and would settle the score, and we call that Bell's theorem. And so Bell's theorem basically says that no theory of local realism, such as local hidden variables theory, so that means when two particles somehow decide upon a value with each other, can account for the correlations between entangled particles predicted by quantum mechanics. So basically, Bell was saying that quantum mechanics is real. And he would notably go on to say that, or the development that would be made as a result of this is something called the CH-SH inequality. It's made by 4 people, Clauser, Horn, Shimoni, and Holt. They're all physicists that came up with this experimental idea that if we can show that entanglement is truly happening if we pass a certain threshold. And in a paper in 2015 in the famous publisher Nature, Henson et al. Were able to build an experiment that spanned over 1.3 kilometers in length in order to remove the possibility of any doubt or loophole arguments about entanglement, and a certain threshold was reached, proving that entanglement was truly going on. So in the realm of quantum computing, entanglement enables this thing called parallelism, which is basically the ability to manipulate multiple qubits at the same time. So without a really good and stable entanglement, you wouldn't be able to operate or do an operation that affects 100 qubits at once, for example. Entanglement enables a lot of different things. Quantum teleportation is helpful. Quantum error correction, which is basically crucial for the use of any quantum computer. So yes, quantum error correction is the foundation of useful quantum computing. And we need entanglement within it as well to ensure that errors are being detected without destroying the quantum computer via measurement. So we want to know that an error is going on, but we don't want to check by opening the box, because then we lose that quantum nature. That's why we need entanglement. And these processes are fundamentally different from classical computers. So if you wanted to use classical bits and you wanted to do an operation that involved many, you'd have to just do it manually one by one. But in a quantum computer, you would only need to perform one operation on an entangled state to achieve the same effect. So quantum computing, as we know, has the potential to save time and computational cost. Another example of entanglement and where it's useful in quantum computing is quantum cryptography. So certain encryption schemes rely upon the preservation of the entangled state. And the way it works is that if a third-party intruder is trying to, let's say, steal your data, the state will break down in the presence of a third party. And so this allows for secure quantum-proof communication, even in channels that you potentially don't trust. And the biggest enemy of entanglement, as I always say, is decoherence, the process where state becomes naturally more and more classical because it's being affected by the external environment. This can be thermal fluctuations, electromagnetic noise, and many other things. Vibrations can break the correlation between 2 or more qubits. Much like balancing a tray of water cups, the more water cups or qubits you decide to entangle and put on your tray, the more fragile the state becomes, and the harder it is to balance. Therefore, it's important to maintain a stable and isolated environment for a quantum computer. This might mean a very, very cold vacuum. And so to read more about decoherence, check out my article on it previously. And so the goal in the development of quantum computers in the future is to develop stable and scalable entanglement. And if we can do that, quantum computers will become completely fault tolerant, allowing for excellent quantum error correction and hopefully quantum advantage. Thank you.